In this lecture, we will first complete our discussion on delta wing aerodynamics, and subsequently we will discuss a little bit on unsteady aerodynamics. So, in the previous lecture we had discussed about the primary vortex and the secondary vortex, and then we also discussed about the fact that there is a flow separation followed by a reattachment, which basically envelopes a vortex structure, and these structures are held very securely, very stably on the upper surface of the delta wing, creating huge suction peaks close to the leading edge, and that is the mechanism by means of which a delta wing sustains lift up to a fairly high angle of attack. And that is why we mentioned earlier also that delta wing is efficient at moderate to high angle of attack. And what happens is that at lower angles of attack, the circulation distribution as per the behavior of the airfoil section is important, while at higher angles of attack for a delta wing, the circulation distribution is not influenced by the 2D or airfoil section behavior, but rather due to the vortex induced lift. And we already discussed about the streamline patterns which are formed on the airfoil section. So, we will continue over to the next slide to sum up our understanding on the flow field and the consequent pressure distribution that is formed on the delta wing. So, leading edge vortices are strong and stable, that we have already seen through the pictures, and because of the high value of vorticity, the local static pressure in the vicinity of the vortices becomes rather small. So, this is basically talking about low pressure, and as you know, wherever there is low pressure, there would be a tendency for a suction created there. Hence, the surface pressure on the top surface of the delta wing is reduced near the leading edge and is higher and reasonably constant over the middle of the wing. So, if you look at the cross section of the wing, this is a pocket, this is another where the Cp is strongly negative, while it may be just moderately negative or maybe even slightly positive on the remaining span, and it is definitely much more positive on the lower side, and thereby the high lift which is created at large angles of attack. The span-wise variation of pressure over the bottom surface is essentially constant and higher than the free stream pressure. It maintains a positive Cp in general. Over the top surface, the span-wise variation in the midsection of the wing is essentially constant. So, this is span-wise variation of Cp, and it is lower than the free stream pressure. That is what we were saying, that it is by and large lower, but it is much lower at these pockets. Near the leading edges, the static pressure drops considerably, the value of Cp becomes more negative, strongly negative. And these effects become stronger, that means the negative sides become further negative as angle of attack increases. Similarly, the positive pressure on the lower side in terms of the pressure coefficient becomes more strongly positive. Of course, pressure on all the surfaces continue to point towards the surface and normal to it, but it is only the difference between the lower and upper surfaces which creates the lift. Leading edge vortices are literally creating a strong suction on the top surface near the leading edges. So, this is the story in terms of the pressure distribution, and as you can understand, there is considerable difference between the airfoil behavior and the finite wing behavior, as we can see it in the delta wing situation. Now, we look at a little bit more on what happens at extremely high angles of attack, and for that we need to first start off with what happens at comparatively lower angles of attack. And here, just for the sake of completeness, I am drawing these structures on the other side of the wing as well. As you know that there is a pair of leading edge vortices, and when you are at a low angle of attack like 10 degrees for example, you have a very stable vortex core, a pair of them trailing down along the leading edges, and they would remain stable far downstream without breaking up. But as the angle of attack increases, let us say at 20 or 25 degrees, gradually what is found is that these vortex cores, they start disintegrating or breaking down or becoming unstable closer to the trailing part of the wing. So, the breaking down may still be happening beyond the wing, but as alpha increases, it gradually gets into the wing itself, and the vortex starts disintegrating, breaking down over the wing. The obvious consequence, as you can understand, will be say loss of lift, increase in drag, etc. And then finally, at extremely high values of alpha, say about 40 degrees, which is significantly larger than the stall angles that we see for airfoil sections, the flow completely disintegrates. So, this is what is called as wing stall. So, there was a beginning of vortex breakdown much earlier, it gradually increased and moved closer to the wing, into the wing, and then it completely disintegrated over the upper surface of the wing, leading to wing stall. So, the suction effect of the leading edge vortices, it enhances the lift on a delta wing, but in a situation like that of wing stall, it completely gets compromised. So, let us read through these few lines. The lift coefficient curve for a delta wing exhibits increase in lift coefficient for values of alpha at which conventional wing platforms would be stalled. So, this is a huge advantage of delta wings, that they continue to generate lift efficiently at high angles of attack, but remember that the lift curve slope will be shallower because of the finiteness of the wing. So, lift curve slope is small compared to airfoil section. Lift continues to increase at large values of alpha. Stall angle is much higher than the airfoil section, and reasonable value of maximum lift coefficient is achieved near stall angle. So, these values of CL may be obtained at much smaller values of alpha corresponding to the airfoil section, but the main issue is that the stall occurs much earlier there. Here the stall is delayed. As far as vortex breakdown is concerned, let us have a little more elaboration on that. That is what we have in this paragraph. So, it is a dramatic phenomena which occurs in the flow over the top surface of a delta wing at a high enough angle of attack. The leading edge vortices begin to fall apart somewhere along the length of the vortex. This is what is called as vortex breakdown, and the vortex exhibits spiral type instabilities closer to the wing tip. So, this is what we started noticing. At intermediate angles of attack, the core twists in various directions, it becomes more disorganized gradually. Further downstream, the vortex core widens, it becomes a much wider structure, and there is a bubble like structure developing, and which finally breaks down, leading to a large scale disintegration of the vortex structures. So, the vortex suddenly bursts, forming a large bubble of chaotic flow. There is significant loss of lift moment, increase in drag, and there could also be a roll due to asymmetric breakdown of the vortices. So, here we just showed the vortex structure gradually becoming unstable on one edge, but similarly, as you can understand, it will happen on the other edge too. and if the breakdown is not happening in a symmetric manner about the two edges, then there could be a tendency for the wing to develop a roll to a particular side, and this effect may start from an earlier angle of attack. It is not at the wing stall angle, but it can happen earlier. So, now we will discuss a bit about unsteady aerodynamics. And what we mean by that? So, when flow properties vary in the flow field as a function of time, then we have unsteady aerodynamic effects. So, any flow parameter, let us say phi, not to be mistaken only as velocity potential, if its time derivative is not equal to 0, then we are talking about an unsteady aerodynamic situation. Let us try to cite a few typical examples. We have discussed some of them already. You may recall in an earlier lecture we were talking about starting vortex. And we said that in the initial phases of the flow establishing itself around an airfoil, the bound vortex grows with time. So, it is essentially a time dependent growth of circulation. Similarly, the circulation shed into the wake also changes with time, and by Kelvin's theorem, the sum of the two always equate to 0. The substantial derivative is essentially 0. So, we are tracking a set of fluid particles within which the vorticity remains conserved, and then the substantial derivative of gamma will be 0. Of course, we are talking about potential flows in the discussion here at this point. Now, the bound vortex achieves an equilibrium value at long time from the time the flow reached the airfoil. This long time may be a couple of seconds at least. So, all that period it remains a function of t, and then it becomes a constant basically. Now, in that situation, if we change u infinity, let us say we increase u infinity, then the bound vortex will again change and it may settle for another value, another new equilibrium where its value is raised. If the u infinity decreases, then the bound vortex settles for another equilibrium value which is lower than the one that we were considering here. So, in this case, if the value increases, we again see fresh counterclockwise wake vortices being shed. If the value on the other hand decreases, we see clockwise vorticity being shed. Based on that shedding, the Kelvin's circulation theorem will remain valid. If alpha changes instantaneously, let us say in the beginning we had a value of, and then at some point of time it changes to alpha 1, then there is a change in alpha which we can indicate as alpha 1 minus alpha naught, and then what is the consequent effect? There will be a change in lift. by the Kutajoukowski's theorem. Again, that will not be achieved instantaneously. There will be a time lag in achieving the lift change, say lift increase if alpha 1 is greater than alpha naught. So, that again is a time dependent phenomenon. So, likewise, we are seeing several instances of time dependent phenomena, which will be reflected in the flow field as well as in the circulations contained in the flow field. There could be other examples, for instance, that instead of a uniform flow, we have a vertical gust, which is modeled using a sine wave, and we can imagine what the response of an airfoil will be when it faces a combination of these velocity components. So, one is the vertical gust, which is a function of space, the other is the uniform velocity, and then the airfoil, as it moves through the combination of these two velocity components, will actually see a time dependent generation of lift because of the spatial variation of the flow field through which it moves. Like we saw for the airfoils, similar effects are created or experienced on a finite wing in time dependent flows, and we can expect that these flow fields will have more complex flow behavior due to the wing tip vortices. So, we were talking about one time changes, that means instantaneous changes of the free stream velocity or angle of attack, etc., but these changes may also occur cyclically. Let us say how they may occur. Let us identify the aerodynamic center, let us say, for as the reference point about which an airfoil section is oscillating, and it is oscillating between two angle limits, alpha max and minus alpha max. So, the airfoil is executing cyclic pitch. In other words, this is a simple harmonic motion that it is executing. So, it has both frequency and amplitude associated with it. So, due to the rapid pitching, there are certain unsteady effects which are created. For example, the CL max that this airfoil experiences is greater than the steady CL max. So, we will use the abbreviation unsteady as US. So, CL max US is greater than CL max steady. Additionally, the stall angle in this case will also be larger than the steady case. That means, you have a situation of delayed stall. This is called as a dynamic stall phenomena as well. Which is different from the static stall. So, let us say that the steady characteristics of the airfoil is like this, where of course, you can understand that this is no longer potential flow, but actual viscous flow that we see in the real world, thereby we see separation. So, let us say this is for the steady case. Then you will find that when it comes to the rapid pitch up case, the characteristic may look somewhat like this, and then when you try reducing the angle of attack, it comes back by a separate path, which means there is a hysteresis. The lift curve, while you increase the alpha, is not the same as the lift curve when you decrease it. So, this is the hysteresis effect which will occur when you talk about a rapid pitching. Near to the leading edge of the airfoil, there is very often a large separation bubble, which is called as leading edge bubble or leading edge vortex. Which is created during the rapid pitching, and if it is held stably without the flow separating off, then the CL max that the airfoil reaches usually gets augmented, or the stall gets delayed, and so on. On finite wings, the leading edge vortex could be wrapping around like this before it leaves from the trailing edge. So, such effects also alter the CL alpha curves of a finite wing. Like we saw pitching, we could also have cyclic heaving. This would be an instance of cyclic heaving. Z equal to 0 is the mean location of the airfoil, and the upper and the lowermost positions could be Z max and minus Z max, between which there is a cyclic heaving of the airfoil. Again, there is some associated frequency and amplitude that is defined over here. Where do these motions occur really? They are often going to occur with a purpose. So, in man-made flyers, the ones which are small scale flyers, typically micro air vehicles, what is often observed is that due to their small scales, the steady aerodynamics that we have already learnt about, say the thin airfoil theory, the Prandtl's lifting line theory, etc., the forces which you can generate from steady aerodynamics are not sufficient for flying the vehicle or perform the desired maneuvers or meet all the mission requirements. Where from does the limitation come? Usually because the flight velocities are of a lower order and more because the platform area is small. As a consequence, you will find that the aerodynamic forces would reduce substantially. Though the vehicle is small and therefore, the payload could be less, the structural load could be less, etc., but still there may be a gap. And that is where flapping the wings either pitchwise or heave-wise or more often in a combined mode, and there could be more modes of motion involved here. For example, sweeping of the wing. That means, the wing executes a movement in this form through a particular trajectory, which we call as sweeping the wing, that is an additional degree of freedom basically. Substantial unsteady forces can be generated. Where do we see this in nature? We see it in birds and insects. Large number of natural flyers, they utilize these unsteady forces to perform their flights, their maneuvers, etc. There are other situations too in larger aircrafts where there could be unsteady movement of the wing, but that is due to different reason altogether. For example, there is something called as wing flutter, wing divergence. These kind of motions are induced by the fluid flow, which energizes the structure. And that basically turns into a flow induced vibration under certain conditions. And in the case of flutter, what we see is that the wing bends about its root and it also undergoes torsion, and they happen in a combination, making the wing to oscillate very vigorously. So, these are phenomena where unsteady effects do surface, but they are unintended and detrimental for the structure, while the flapping on the wings in miniaturized flying vehicles, man-made flying vehicles, or as they appear in nature when birds and insects fly their flap their wings and fly through the air, are intended unsteady effects. So, with this we come to the end of this lecture, where we discussed further on delta wing aerodynamics, and then subsequently we very briefly discussed about some aspects of unsteady aerodynamics and how it can apply to both airfoil and finite wing sections. This included the different kinds of kinematics involved and the corresponding aerodynamic response. Thank you.